Many thanks, Leslie, and many thanks for everybody who has joined today. As Leslie said, this is going to be very much an interactive session, so it's not just a case of you listening to me. We will be running 3 polls during the first quarter of this presentation, and we would like you to answer the questions when they appear on your screen. We will publish the results of those questions as well. So if you've got a group of people, just have one person to leap over and use the mouse to answer the questions when they appear on the screen. Let's talk about the premise for this whole presentation this morning, and that really is that modelling has become a prerequisite for understanding what is happening in the urban environment and understanding the impact of flooding. Now, it's really government directives that are driving a lot of this, and those government directives are dictating that utilities and cities need to understand the assets that they're responsible for and need to take responsibility for controlling those assets and controlling the way that they perform. And classically, that will be done by creating a hydraulic model. Now, it would be very useful for us to understand if those people in the audience today are already in a situation where you use a hydraulic model, and in particular a hydraulic model from InfoWorks. So if you could look at your screens, there's a very quick yes/no answer question coming up. Could you give us an indication from the people who are currently in on the meeting, how many people currently use an InfoWorks modeling product of any sort? So we'll give you 10-15 seconds to answer the question, and we'll have a look at the breakdown of the audience in the webinar today. As Leslie said, we do have well over 1,000 people registered today, so it's going to be a pretty wide-ranging poll that will allow us to see exactly what is going on. Okay, I can see the answers beginning to tick by on my screen, so everybody's obviously being very good and answering those questions. I'll close the poll at this point in time. You're going to have to be quick on this. There's no hanging about, so we'll close the poll on this, and we'll have a look to see what the split is of the audience today. And it's a very interesting split. You can see that we have almost 3/4 of the audience are actually have used an InfoWorks product, but 30% if you haven't, which is really good, and that's excellent to see. So we'll take that as a big plus, and we'll move on with the presentation. So bearing that in mind, let's have a look at what it is we actually need to do with hydraulic models and what we're trying to ascertain. What the hydraulic models need to do is to essentially work out what is actually happening on the catchment. Now, when it comes to urban flooding and urban inundation, it comes in a variety of different formats. And so our models have to be able to adapt to all of the different sources of flooding that can potentially happen on a catchment. And if you're going to do this properly, you need an integrated catchment model. And that's really the premise for today's talk. So if we use these pictures on the screen here as a prompt to what might be going on. If we take the picture on the top left, for example, this is a very common scene. We've all seen this either with our own eyes or on the news. Short, sharp storm, either summer or winter, which causes inundation on a road. Typically, the road gullies aren't able to cope with the excess rainfall. The runoff produced is far in excess of what the system can accept at any given time, and we end up with street flooding. And providing the people don't drive their cars through those roads at high speed, generally speaking, that street flooding can usually be kept within the curbs. Obviously, if people drive vehicles through at high speed, it can create a bow wave, and that can then impact on properties in terms of the waves going up against the buildings and potentially entering the properties. But that is essentially stormwater and doesn't tend to have a quality element to it. Picture top right, we have the classic example of a sanitary or a combined system failing and flows being discharged to the surface as a result. In this particular case, it's actually the manhole's discharging in a local woodland area, and you can just see there's a small path to the left of the manhole, and people jog along that path and cycle along that path. So obviously flows discharging from that sewer are unpleasant at the least, and potentially a damage to human health at the worst. So we want to try and address those sort of issues. They are quite localized, both of those issues. At a bigger scale, we then have the situation where we can have citywide flooding, which we can see in the bottom right-hand side. And these sort of events are typically caused when there is a catastrophic event, say a reservoir failure or something like that, or if a sea defense is breached and the sea is able to enter the nearby towns and cities. We get mass inundation of urban areas in that way. The final one I want to highlight is one that perhaps we don't think about so often, And that is a sort of semi-local issue. In this particular case, we have a car park, and there's a serious rainfall storm going on. The runoff generated on that car park is running over the overland, and the water is being discharged into a local watercourse. And you might initially think that that isn't actually too bad a situation. The water is essentially being taken by the watercourse and carried away. But you have to bear in mind that that's a car park, and cars park there, and oil and other residue from the motor vehicles gets deposited on the car park during dry weather, and then when it gets wet, that pollution is essentially picked up and washed into the local watercourse. So not only do we have a hydraulic problem on that particular example, we actually have a water quality issue going on as well, and that can be, that can be equally as important to model. Now, these are all very different types of events, and classically in the past, we've actually used different types of models to look at those individual types of scenario. So what I'm going to do is put another poll up on your screen at this particular point and ask you if you could just give everybody here today an indication of the types of model that you use at the moment. Obviously, for those of you who either haven't used an Innovyze modeling product in the past or perhaps don't do modeling, then please answer the question accordingly. But let's have a look at how the breakdown of our audience today splits across the disciplines of wastewater, stormwater, and combined systems, and perhaps river systems as well, because we will be talking about river systems today. Okay, we'll just give you a couple of seconds to think about that. And again, if you're not sure, if you don't have any modeling experience, that's not a bad thing. That's not a bad answer. So please be honest with us there. And that's probably one of the reasons why you're here with the audience with the webinar today. Okay, I'm going to close the poll at this particular point. As I said, you have to be quick on these things. So let's close the poll and share those results with the audience. And it's a good result. We're seeing a very even breakdown of the audience today as to who's been involved in the different aspects of wastewater modeling or stormwater modeling or combined system modeling, and a good percentage of people get involved with river modeling as well, which is really good to see. The people who've not done any modeling, you are very welcome, 12% of you today, so that's a good number. Good to see you here, and hopefully you can take on board some of the things that we're going to be looking at today. Let's hide that now and move on with the rest of the presentation. So let's carry on with that and see where we're going. Right, let's go back to my PowerPoint slide. Right, okay. So that's where we were, and we were looking at those different aspects of the different types of models that you can do. Okay, so let's have a think now about the interactions that we get on our above ground systems and our below ground systems, because this is how we can start to get involved in the whole integrated modeling process. So let's have a look at what's involved. Good percentage of you have done stormwater modeling in the past, and that was good to see. And in those sort of models, we're classically looking at the performance of the underground stormwater network, and we're looking for failure points. And failure points will particularly present themselves as overland flow running down the roadways. And the screenshot that we can see on the left-hand side of the screen is a small urban area. It's actually down in the southwest of England in the Torquay area. And my thanks to the team at Torbay Council, who are one of the lead local authorities down there, for allowing me to use their model for this presentation today. And we can see in this example, the team down there have been looking at the potential inundation of one of the main roads that runs down through the area in Torbay, and there is a high density of housing and shops which are all potentially at risk as a result of any flooding that happens in that particular main road. On the right-hand side of the screen, we have another example, this time of a river system, of a river model, and it's good to see 40-odd% of you have done river modeling in the past. And here we're not just as interested in what's happening in the river, but we're more interested perhaps in what happens when the river doesn't have capacity to carry all the flow. And as a result, the banks are inundated, and we end up with overland flow going into the either defined floodplain areas or finding their way into urban areas. And in that particular screenshot, we can see of the two panels in that screenshot, over on the left-hand side, water is going into the floodplain as we would expect. Unfortunately, an amount of it does in fact go the other way and ends up in the urban area, and we end up with housing in some of the houses being flooded. And we can see there's quite high velocities. There's some small velocity arrows shown there, showing where the water is classically going as it flows over land. Now, in the past, we've dealt with those two types of scenarios separately, and I think some of the results in that past poll reflect that. what we really want to do, if we possibly can, is to deal with those two scenarios as one, because in reality there are interactions between the rivers and the drainage network. Any high levels in the river will prevent the drainage network discharging, and any discharges in the network into the river could potentially be sources of pollution, as we saw in one of those screenshots. So we do need to understand what's going on there. And that's actually quite a difficult mathematical challenge to do. Even in separate models, it can be difficult. But if you put the two together, that's a much bigger mathematical challenge. And the reason it's such a big mathematical challenge is that when we have interactions between what's happening in our man-made drainage networks, so in our sewer networks, in our stormwater networks, and indeed within our managed river channels, the mathematics involved in looking at the water in those carriers is essentially one-dimensional mathematics. We don't have to worry about a directional component. The pipe will determine which way the water goes, or the river will determine which way the water goes. But once the water leaves those structures, once it's exiting the underground pipe network via flooding at the surface, or whether a bank is inundated on a river system, we need to use an extra set of mathematics. We need to use 2D mathematics in order to ascertain what is happening and how that flow is traveling over land. Now, InfoWorks ICM it was the first application in the world to put together the two different modeling disciplines and to have both the 1D and the 2D mathematics as one. In the past, people have done these things in isolation. They've not done it together as one particular thing. Now, our final question that we'd like to pose really to the audience today is really whether you as an attendee have been working with properly fully integrated 1D, 2D catchment models in the past, or whether you've essentially been working in isolation. So let's just give you a couple of seconds to think about that and to answer that for the audience, and that is going to determine how we're going to essentially deal with the rest of the webinar today. Okay, so that's probably enough time. You've had a good chance to answer the questions there, so let's close that poll down and then share that result with you. And it's almost a 50-50 split, which is really good to see. So half of the audience today have traditionally been doing single discipline modeling, and the other half of the audience have already been involved with some integrated catchment modeling. And that's really good to see, actually, and that's a really good result. So thank you everybody for participating in those particular polls that we've had going on today. So that's really, really good. Okay, let me come back to the presentation, and we will move on and go forward from here. Okay, sorry, the screen's just going to flick around very briefly for you while I flick between the polls and the questions that we've been having. Okay, so let's move on and actually think now about integrated catchment modeling and what's actually involved in that. When we're doing the whole 1D, 2D modeling of the system in one complete package, as it were. Okay, so up on the screen we've basically got a couple of examples here, and one is real and one is not. Okay, the first one on the left hand side of the screen is not a real model. It's actually one of the models we created when we were first making sure that integrated catchment modeling, where we're putting together the different types of catchments and we're putting together the different mathematics, was actually feasibly possible, was actually doable. So it's a prototype. And the other example we're going to look at is one of the first integrated models that was actually created here in the UK. So over on the screen on the left hand side of the panel, let's just have a look at what the model is trying to do. I say this is not real, this is essentially a prototype model, but what we're trying to look at is a representation of a river catchment, which we can see here. A urban catchment, which is represented here. The blue polygons are representing buildings, the grey lines are representing roadways, and the green dots that you can see there represent the manholes for the sewer and stormwater network that's underneath that particular road. The spider web that you can see surrounding the whole model is our 2D mesh. So for those of you who have not done 2D modeling before, this is a bit like a blanket. It's a mathematical representation of the way the undulations in the ground occur, where we have steep slopes and where we have flat areas of the ground. Okay, and what we want to be able to do in a fully integrated model is look at the interaction between the sewer network for the urban area, the river network, and the surrounding catchment, which is both gathering runoff and potentially acting as storage. So what we have to imagine is that now there's an enormous rainfall storm that actually occurs on this catchment, and what we want to see is what happens when the rainfall actually starts to land on that catchment. So initially we see a large amount, a very quick response in the urban area, and some of the buildings to the top of the catchment do experience a degree of stormwater flooding as a result of the water not being able to reach into the network in time. As time goes on and potentially the rivers take a longer to react, we see the river fills up with water and the floodplain comes into action on the left-hand side. However, the floodplain is not sufficient to store all of the water in high flow situation, so the river breaks bank on the other side, and we now have the urban area being inundated by river water. And in fact, we have the scenario now where river water is entering the sewer network through these manholes here, and is actually being transmitted down the sewer network, and we actually have river water being ejected from the underground network and actually coming out here. And the reason it comes out here is that the pipe network has been surcharged by the high water level in the river here, so the water can't get into the river in the natural way that it would expect, so it's exited onto the ground here. Now, as I say, that's a pilot model, it's a prototype model, but it was built to ensure that we could actually put together the one-dimensional and two-dimensional mathematics, and that underground pipe network systems could be made to interact with river systems. Okay, and that was the theory, and it was really good to see that the theory did in fact come into practice. But it's not all about theory and practice, it is about doing it in reality, and that's what we have for the model that you can see over on the other side of the screen. What we have here is a real network. It's a small model, but it's completely real. It's actually based up in North Wales, and my thanks here to the local council in Conway in North Wales for allowing us to use their particular network in this particular presentation. And what we have here is a representation of the nature of the terrain in Wales, which most of you will be familiar. If you're from an UK audience, you'll know that Wales has a lot of steep hills and mountains, and this is classically what we have here. So water will run off this catchment very, very quickly and will essentially end up in the township, which is located at the bottom of the valley. This is actually quite a nice part of Wales. It has a very nice view. People will pay a significant amount of money for this particular type of property because the aspect out onto the open land and the river is very nice indeed. However, when it rains, they do get some issues that actually happen in the catchment. And in fact, some of the people who live in the properties down here do experience a degree of stormwater flooding because the gullies aren't sufficient to take up the flows. So very similar to our little prototype model. Unfortunately, they also tend to get hit by the river system. So if we play the animation here, we'll see that it's raining and time starts to tick by. And what essentially happens is that after a short while, the local areas here start to experience a small degree of localized stormwater flooding. That stormwater flooding can actually escape into the local field, and essentially as a result of that escape prevents the properties being flooded to any significant effect. However, as time goes on, the river will fill up, and the area that you can see actually starts to fill up with flood water, which is what we want. Unfortunately, the other area neighbouring the town also fills up if the bank is inundated. And at this particular point, the escape routes that were put in for the stormwater to leave the buildings and get into the field now acts in reverse. And as a result of that escape route, we actually have a reverse situation, and we have river water that is able to get into the properties and cause flooding, this time as a result of river flooding rather than as a result of stormwater flooding. And the local council in the area needed to build this model in order to ascertain exactly where the risks were. Where was stormwater causing an issue, and where and under what conditions was river water causing an issue as well. So that's an absolutely real life model. And what I would draw your attention to is actually it's quite a small model. There are very few nodes involved. You can see the green dots representing the nodes. The cross sections in the river are there to represent the shape of the river, but that's actually quite a small model. You don't need to have a great big model always to conduct a study. Sometimes the smaller versions of the software will be absolutely sufficient for what we need to do. Now, in both of those cases there, those were animations, but I think at this point it's worth just summarizing what we've discussed so far. So really, as far as InfoWorks ICM is concerned, what we're looking at is the full interaction of 1D and 2D mathematical processes. So we need to be able to, in software at a technical level, put together those two very different types of mathematical processes and make them act as one, because that's what happens in reality. In reality, what happens above the ground and what happens below the ground is all happening at the same time. And all the bits of the catchment need to be able to model as they actually are in reality. And that's what we can actually do with InfoWorks ICM. Both the hydraulics and the hydrology come together as well, because again, it's all one catchment. And if we're producing a hydraulic model, that needs to all be able to be set within the single model. Why do we want to do that? Why is that such a grand ambition? Well, because what we really want to do above all else as engineers is to really understand all of the processes that are happening at any particular given time. And if we have a single fully integrated catchment model, we can do that. That is a perfectly acceptable aspiration to have, and it's perfectly possible to do. Okay. On top of that, because we're using one software application to do this, we suddenly provide ourselves with a much simpler solution. We're only having to learn one piece of software. We're only having to use one piece of software. And so from an engineering perspective, particularly as a consultant or as a utility, we have a much more cost-effective solution to something that in the past we perhaps shied away from because it's considered to be a very complex engineering challenge. With the software that we have today, the engineering challenge is still complex, be under no illusion, but we can take a much more simple approach and a much more cost-effective approach to what we're doing. Now, the examples that I put on the screen just now were obviously animations, just in terms of time. But what I want to do now is to switch over from our animations and from PowerPoint. I want to leave that behind, and I want to show you the actual real software that we have going on. So I'm going to change my screen at this particular point, and we're going to move over, and we're actually going to show you InfoWorks ICM for real. So this is the absolutely real live software. And what I'm going to do for the next 30 minutes or so is to take you through some example models where I want to focus in on the aspects of integrated catchment modeling that we've just been discussing for the last 15 minutes or so. So I'm going to be looking at a series of real models, and I will give credit to the various organizations and individuals who were responsible for these models, because they have been kind enough to allow us to use them in this presentation and for other purposes as well. So I will make credit to them where they come up. So I'm going to take you through, and we're going to start at the very beginning. So this is really for the benefit of the people who've not done hydraulic modeling before, or perhaps for the people who've just done single discipline modeling. And we're going to take it through from a very simple classical 1D model. We're going to go right through to the much more advanced sort of overland flow modeling, and we'll look at them all. In every case, I'm going to be showing you real models. That I always feel is important so that people understand what's going on in the catchment. So let's start, and let's start by the one that you can see on your screen at the moment. I make no apologies for the fact it's a small model. As I said earlier, small models can contain a lot of detail, and they can be very, very good at showing you where actual incidents are occurring and pinpointing incidents because you have that sort of nice small size. This particular model is right up in Scotland, so my thanks to the team at Scottish Water for this. And what we have is the classic model. For those of you who've not done hydraulic modeling before, what we're looking at is a series of manholes. They're shown in green because at the moment those manholes are behaving correctly, so they're performing correctly. We have buildings, which I've highlighted in red, and those buildings have actually, the position of those buildings and the shape and the size of those buildings have been extracted directly from the GIS system. And InfoWorks ICM works coherently with Esri's ArcGIS system and also with the MapInfo GIS system. So those buildings and properties are being shown in the red color from the GIS, as is the gray outline that you can see in the background, just to give some extra definition to what's going on. Obviously, between the green dots, that is the pipe work for our particular model. Now, as I said, that mapping data actually comes from the Esri system, but these days there is actually quite a lot of mapping data that is available completely free of charge. One of the great advances that we've seen just in the recent couple of years is the availability of OpenStreetMap. That's a completely open source mapping system. It's available directly from the internet, and as long as you know what your OpenStreetMap web address is, we can use web map services integrated with InfoWorks ICM. So what I can do is I can change my GIS layers to be layers that are brought in from OpenStreetMap, and I can just drag that map definition in from the internet, and it will immediately show on the system. And I can mix and match, so I can have my layers both as OpenStreetMap, but also as the layers from the GIS system. So if I drag the layer that we have here, we now have a combination of the GIS layers showing us the properties and OpenStreetMap showing us what is going on. So here's the properties for the roads and the roofs. Here's my background grid, and here's my OpenStreetMap. So that's a really nice innovation, and being able to make use of open source data, I'll come back to it later in the presentation, is a very powerful attribute. So if you don't have GIS data available, don't panic. Go to the internet, use the open sources that are available. So what do we want to produce in this model? What do we want to look at? This is a 1D model. This is a classic 1D model. For those of you who've done modeling for many years, you may be familiar with products like InfoWorks CS, perhaps even HydroWorks from many years ago. They are all 1D models, and they are 1D stormwater models. And what engineers and practitioners would classically be looking at is to try and identify where there are failure points in the system, either in terms of inundation at the surface because of a failure for the pipe network to transmit the flows, or just incapacity in the pipe systems themselves. And we can use themes throughout InfoWorks to show that. So we can see here the manholes that are currently discharging water to the surface, and there's at least 4 locations near to the sea. The sea is this area out here, near to the sea, where water actually doesn't make it to the stormwater outfall, it actually discharges to the surface. A smaller location found over here. So we can use these models to ascertain exactly where all that flooding is essentially happening. But all of the 1D models can really do in reality is show where that flooding starts, where it actually gets out of the network and onto the surface. What we can't see in a 1D model is where the water goes once it's hit the surface, okay? And that is where our 2D models start to come into play. So let's shut that model down and let's look at a classic 1D, 2D model that actually exhibits that particular type of scenario. So let's have a look at that and see what's going on. So I'm going to open up a model now, which is, as I said, it's a classic 1D, 2D model. And I'll open it up and I'll make it go full screen just so we can see what's going on. Again, it's not a huge model, but the detail that we get out of it, as you'll see in a moment, is very, very clear indeed. Let me perhaps change the view very slightly to something that the majority of people will be slightly more familiar with. So I'm going to turn off the 2D area that this model has and just look at it as the classic 1D model. And so you can see, I hope now, again, the green manholes, because everything is behaving okay at the moment, the grey underground pipes, and we're using here some map info data in the background to show us where all the buildings are and where the roadways are. Now, this model does experience a degree of flooding as well, okay? But this is North London, so my thanks here go to the AECOM as they are now, but it was Faber-Maunsell when this model was originally created. A chap called Richard Siebert, I worked very closely with Richard to produce this model. This was back in the very early days, actually, of when we had 2D modeling, and we were looking to try and experiment with rolling ball methods in GIS to work out where overland flows went, and we wanted to really see if InfoWorks could provide a much more streamlined solution to that. So what we did was to take the model, the 1D model that Richard had already built, and basically see if we could enhance the modeling to look at overland flow as well. So we add this extra polygon with this sort of spider web in the background, and that allows us to pick up the terrain and the way the slope is and where all the buildings are. And now when we look at our worst case scenario, we can see there's an awful lot of failures of the manholes in this particular model. And as a result, there is overland flow. And let's just zoom in on the center of the model to see precisely what's going on. So the water generally, being North London, the roads tend to have very high curbs. Victorians knew a thing or two about hydraulic modelling. And the high curbs actually work to actually contain the flow in the roadways quite well and prevent it actually escaping onto the pavements into properties. And for the most part, they do exactly that in this particular model. A lot of the water exiting from the manholes in the model is able to simply run down the road and essentially follow almost the line that the underground sewer network takes. But there is one very obvious location here in the center of the model where that doesn't happen and where the water actually exceeds curb height and ends up flooding the front of these particular properties that we have here. One of the most common reasons for this particular scenario is when councils come in and put in drop curbs so that people can actually more easily cross the road, particularly if they're in mobility scooters or have prams or have kids with scooters and things like that. Dropping down a curb that's 4 or 5 inches deep isn't practical if you're on a wheeled trolley of some description. So council puts in a drop curb to try and help, or residents put in a drop curb so they can take their car off the road and park outside their house. Unfortunately, what's good for wheeled vehicles and wheeled transport stormwater is also very good for water, and that's exactly what happens here. So the water is able to actually come up and actually comes up against the property. Not only that, it goes between these two properties, actually travels overland at the rear of the properties, causes overland flooding and a little bit of inundation on the garages that are on this minor back road, and actually the majority of the water ends up ponding here at the back of these properties. So these properties experience flooding, not because there's flood water at the front of their house, but actually because there was an incident some distance away. But the overland terrain and nature of the terrain means that any water exiting the roads over here will actually find its way here. And we can not only look at that as a worst case scenario, but we can actually look at that in an animation. So just as we saw with the model in Conway, I can make time tick by now. Water exits the manholes, water finds its way between the properties, floods the garages behind the houses to start with, and works its way over, and eventually over a period of an hour or so will actually congregate and cause flooding at the properties that we have here. So in terms of understanding all of the interactions here, we're just understanding the interaction between the surface and the underground network in this particular model, but we can see very clearly where water goes. We can see properties that are at risk of inundation, and in this particular case here, the darker color blue for the different elements in the 2D mesh, the darker the blue, the deeper the water. And we can actually use the software, and we can actually get the relative depths in each one of those elements in order to see how it compares with property levels. And those of you who've done risk modeling will know that in terms of flood depths, we're kind of interested in numbers of around about 300 millimeters. Any depth higher than that, and we are starting to have the potential for water to enter underneath properties through air bricks, or perhaps even over the property threshold through the doors and inside the properties. So we can actually zoom right in if we want to. We can go right in on the properties, and we can look at the individual depths in these individual elements if that's what we want to do. So we've moved on. We've really gone through, and we've essentially taken what used to be just very simple 1D modeling, and just by adding an extra layer, this 2D layer, and adding information from our GIS, we can now start to get an appreciation of what's happening above the ground as well. Now, if we can do that for our drainage networks, then there's really no reason why we shouldn't also be able to do that for our stormwater networks as well. And if we're going to talk about stormwater, then we can also perhaps talk about river systems. So what I want to do is to now show you a system, and I haven't shut the software down here, you'll notice. I'm staying fully within InfoWorks ICM the whole time. But I want to now show you a completely different model, and that is a river model. And this is actually, for any of you who've done the river modeling, there was a good percentage of you who had done river modeling at some point in the past. This is what a river model would classically look like in InfoWorks ICM. It looks obviously very different to our sewer networks, but actually it isn't that different underneath the actual mathematics. We're still looking at modeling water in channels. So what I've done here is just to drag on the LiDAR data. So this is the actual surveyed land formation data, as opposed to the mesh that we were looking at just now. This is actually a 1D river model. So this is the sort of thing that other people might well have done in, say, products like HECRAS or Flood Modeler Pro, or ISIS as it used to be known. 1D river models. And we can do all of this same type of modeling inside InfoWorks ICM very quickly and very efficiently, and actually very easily as well. And what we can do is make a representation of our river system. So running down the middle of the screen, we can see the center line representing the river, and we have the cross sections. And you saw this in the model of the Conway model as well. So these are the individual cross sections that we have in the model, and we can look at the detail behind those. So we can just pick up, let's take this section right at the top here. We can actually look at the river sections in the model, and we can see how each one of those sections, and I can then work through each section in the model and look at the individual left to right bank situation. Now in this model, not only are we modeling the river channel, which in this case actually has a split in it as well, but we're modeling the floodplains as well. So this is a pure 1D flood model that we're looking at here, and we've got the whole definition of the river running all the way up the system. And what we want to know is essentially where the river is likely to be inundated when we get into a high flow situation. So all I've done is I've dragged on one of my flood mapping themes, and this is one of the standard themes we have in InfoWorks that allows us to look in an almost quasi 2D situation at the potential results of flooding in this model. So this again is a maxima that I'm looking at here. And we can see very clearly where the river is. Again, we're using the blue color to indicate the depth of flooding in the catchment. Deeper the blue, the more water there is, or the more depth there is. But this isn't a 2D model. This is a 1D model. And what we are doing is essentially using the 1D results that we have at the individual cross sections, and we are extrapolating into the dead space to extrapolate a potential water depth based on a known water depth at 2 of the corresponding cross sections. So we have actual hydraulic results on this cross section, actual hydraulic results on that cross section, but an interpolated result here. We can sort of see the likely degree of flood spread. Now, in this particular model, it was built because the people concerned wanted to essentially look at the protection device that was put in here to divert the river water away from this particular area. And it did a pretty good job at diverting the water away. Unfortunately, it was done without a hydraulic model, and as a result, the water didn't disappear. It had to go somewhere, and actually the water gets forced into that area by essentially doing a U-turn at the north of this catchment. But we can do these sort of things with our river models, and as we did before, we can also use our models in a sort of more animated fashion, and we can allow time to tick by, and as time ticks by, we will get different levels of inundation in the catchment to show us the different degrees of flooding. Now, one of the things that river catchments have, which makes them a little bit more difficult to deal with than the traditional urban catchments, is that people tend to introduce other structures into networks. And in particular, we quite often find structures such as bridges. And in this is exactly the same model, but in this section here, we can see that we have a bridge. Now, I could tell you that this is a bridge, and I can basically go through and describe the elements of that bridge to you, and you could perhaps imagine it in your mind. But one of the things we do with InfoWorks is we try wherever possible to actually allow the software to visualize things as well as we can. So let's add the water to the model as we had before. And now I'm going to use the 3D tool that we have at the top of the network here, and I'm going to put my model into a 3-dimensional view rather than a 2-dimensional view. Okay, so we don't anymore have to imagine what our bridge might look at. We can now actually see what our bridge will actually look like, and we can basically ask the software to create, from the numbers and from the numerics and from all of the data, we can ask it to create the model of our bridge. So we can see the incoming flows, we can see the arch of the bridge, we can see the deck of the bridge, we can see everything that essentially the mathematics will see when it comes to processing. And for those of you who like computer gaming, you'll be very familiar with these sort of fly-through ideas that we have. I'm not a particularly good computer gamer, so my skills in terms of 3D navigation perhaps aren't as good as others would be. But here we are simply using the tools that the software provides to produce a visual representation of what is essentially an above ground structure. So we really want to see what's involved in our system, what's involved in our network, but we want to do it visually rather than relying on the sort of more classical picture that we had here. Okay. Now again, I've been opening up all these models, and I haven't been actually shutting the software at all down through. All of the windows are still open. I can navigate through all of the different displays, and I can keep my 3D view up, or I can keep my view up before, or I can go through and I can shut down all of those views and leave me with my working space. Now let's take that scenario that we had of our river model forward and say, well, that was a river model that was done purely in 1D. So we weren't using any 2D aspects at all. We were just using one-dimensional modeling, and we were basically modeling the floodplain in 1D. And that's what we've had to do for the last 20 years or so. But we did it on the understanding that perhaps it wasn't as accurate as it could be. And if water comes onto the surface, as we saw with our urban flood models, then really we want to use surface modeling if we possibly can. So in this fourth example I want to show you, this is again to represent the potential catastrophic failure of a dam. Of a reservoir, and we want to understand where the water goes if it's no longer contained by the reservoir. Now this is a real model, but I would stress that the actual scenario I'm going to show you has obviously never happened, and hopefully it never will. But agencies, water companies, Environment Agency, whoever they may be, they have been asked by government to essentially evaluate the potential catastrophic impact of a failure of a major asset. And hydraulic modeling is a very good way of doing that. So in our model, we are representing the reservoir very simply by a very simple 1D storage area up here, which is full of the reservoir water. There's no other 1D network in any of the model you're looking at. What there is a 2D zone that is covering the valley that runs here and the whole of the township that you can see below. And the only thing between the reservoir and the township is a major road and some large factory type buildings that we have here. Now, the 2D model was built so that the 2D mesh would be used to route the water exiting the reservoir and being used to look to see where everything goes. So if I actually play my animation, here we are actually routing the water over land using a 2D mesh. Now I've turned off the spider web so you don't see the spider web. All you see is where the water actually is. And the triangles that we're using for our 2D mesh here are very, very small, which is why you can't actually see the individual triangles. We're using a very, very detailed model here. But what we want to see is where the water goes if it should escape from that reservoir for any reason. Now, obviously, this is interesting from both a hydraulic perspective, but these models are also built not just for understanding what the water depths are on a catchment and the speed of the flow and the extent of the travel of that water, but they're used typically by emergency planners. Because the emergency planners will be the people who will be first on scene should there be a catastrophic event, and we really need to understand which people are at risk and which people aren't. Okay, so in this particular model, what we can see is that if we have to respond to this type of emergency, we don't necessarily have to clear people very far from the area. Anybody living in these properties are likely to be affected, but they only need to be moved a small distance north because the houses and the people up here are not likely to be affected. So our emergency plan might well be to make sure that we have time and we have procedures in place to move people from these properties to this area of slightly higher ground up here, where it is very unlikely that they will be impacted by a failure of that reservoir. The other very interesting statistic, if I run that through again, is how quickly the water actually impacts the building that we have here. The water is about to hit the building now, and it does it in just under 5 minutes from the failure of the reservoir. So really the emergency authorities will have very little time to react. They have to have a really good plan to protect those people. The interesting point is the building, the big factory, is actually protecting a number of properties that are directly behind it. The building acts to divert the flow left and right, and so actually anybody here is not potentially in as much danger as people just a little bit away from the building. So that's another use for an integrated model. In this particular case, we're integrating our reservoir with our big surface model. And hopefully those 4 models that I've shown you will give you a flavor of what people are doing. I want to finish the look of the models at one that I think is very special because it's a quite unique example. I was provided it by Atkins Consultants, to my thanks to the team, the modeling team who are located in Derby, who allowed me to use this model today. And they were looking to see if they could use their existing InfoWorks licenses to even more innovative type structures. And here they built a model which they extracted the data directly from CAD, and they wanted to see if InfoWorks, with all its 1D and 2D capabilities, could actually do something that they classically did with CFD software. So here they have managed to produce a model, a pure 2D model of an overflow chamber. And we have the chamber coming in. This is where the water comes in. The dots that you can see are essentially monitor points, so we can look at the depths in the channel. This chamber and this channel have a circular bottom. The main channel appears here, and basically everything accumulates in this catchment and comes through, and these are baffles in the chamber which divert the flow into these pipes. There are storage control devices here. Now I can describe that to you, and hopefully most of you, particularly with engineering background, will be able to visualize, I hope, what we can see there. But if we put that into our 3D view, which we saw before, which we used before to look at our bridge structure, we can use our 3D view to actually look at our chamber as well. So here is the main chamber. Here is the pipe and the half pipe of the channel that's coming in. Here are the baffles which divert the flow. Here is an emergency weir which will drop water into the chamber over there. And then we have our control devices which regulate the flow from the chamber. So here we're using a package which perhaps people traditionally in the past have considered to be for stormwater modeling or for river modeling, and here we're actually using it to do quite detailed analysis and quite detailed design perhapsly of our chamber. And as part of that design methodology, there may well be lots of different scenarios. It may well be that the baffles don't work particularly well in the initial design, and so we have a feature in InfoWorks which allows us to do what we call scenarios. And basically, scenarios are the same model, but with slight differences. So here we've added some training walls, so we can try and use the training walls to divert the flow. Here we've amended the apron into the actual channel itself. So we can look at these different scenarios. I'm not having to drag and drop anything from the database. I can look at it here. And of course, if I put those training walls in, I can then put it back into 3D, and we can see where those training walls are in the model as well. Okay, so basically we've looked there in the last sort of 30 minutes or so at integrated catchment modeling. We've looked at the different types of networks that have been created, and I've finished with what I hope you will agree is a very interesting additional modeling scenario, which I wouldn't have thought about myself if I was there. So that really concludes the talks that I wanted to do today, and it also concludes the presentation of the software. And I hope you enjoyed looking at some of those models. My thanks indeed to the various organizations who were kind enough to provide them for today's presentation. Without you, really, people would not really have such a good appreciation of what people are doing and the boundaries people are pushing.